Let's talk about what might just be the single most important unsolved problem in all of mathematics. Seriously, it's a mystery that connects pure chaos to a hidden perfect order. And hey, there's even a $1 million prize attached, so, let's dive in. So, where does this all begin? Well, it starts with a question that seems almost childishly simple, but has stumped geniuses for centuries. Are prime numbers random? Is there any pattern, any rhyme or reason to how they pop up on the number line?
I mean, just look at them. Sometimes they're right next to each other, like 17 and 19. Other times there are these huge deserts between them. For thousands of years, this just looked like noise, a total mess with no discernible pattern at all.
So here's our game plan. We'll start with the riddle itself. Then we'll look at an incredible map created by Bernhard Riemann. We'll find the secret of its most important landmarks, the zeros. Then we'll get to the $1 million hypothesis itself, talk about why it's so important, and finally, take a look at the massive, ongoing hunt for a proof.
Okay, first up, the riddle of the primes. The real problem here isn't just finding the next prime number, it's about seeing the bigger picture. Can we predict how they're spread out?
The greatest minds in history looked at this problem and were just stumped. The primes behave like this stubborn, cosmic code that no one could crack. But then, in the 19th century, one mathematician stumbled upon a key that seemed to reveal a hidden and, frankly, unbelievably elegant structure.
And that brings us to our main character. In 1859, a German mathematician named Bernhard Riemann published this short, only 8 pages long, paper that just turned the whole field upside down. He didn't solve the riddle, not exactly. Instead, he drew a map to a secret world where the primes suddenly made sense.
And this map is called the Riemann zeta function. Now, don't let the name scare you off. All you need to know is it's a tool. You plug a number in and it spits another number out. The magical part is that this function, which doesn't seem to have anything to do with primes, somehow contains all of their secrets. Think of it like this. If the prime numbers are individual musical notes, the zeta function is the beautiful, complex symphony they create. The function's shape is literally dictated by where those prime number notes are.
So if the zeta function is our map, what should we be looking for? Where are the landmarks? Well, the answer, weirdly enough, is in the places where the function's value hits 0. These are the key locations that guide us through the landscape. So what exactly is a 0? It's just a number you can plug into the function that makes the whole thing equal 0. The best way to picture it is to imagine that our function creates a giant 3D landscape with mountains and valleys. The zeros are all the points that are exactly at sea level. Now, it turns out there are 2 types of zeros. The trivial ones are, well, they're boring. They're predictable, easy to find, and they don't tell us much. But the non-trivial zeros? Oh, they are the interesting ones. They hold all the secrets about the primes, and figuring out where they are is the whole point of this mystery. So Riemann starts calculating where a few of these special non-trivial zeros are, and as he plots them on his map, he sees something. Something so shocking, so perfect, it had to be more than a coincidence. In his paper, he was almost casual about it. He just wrote that it's very probable that all these important zeros, or roots, have this special property. He even admitted he couldn't prove it after some fleeting, vain attempts, but you can tell his intuition was screaming at him. He saw the pattern. And here it is, the big one. To picture it, think of a flat grid, a map. Every one of those special, non-trivial zeros has a coordinate on this map. The Riemann hypothesis claims that every single one of them, an infinite number of them, all lie on one single, perfectly straight vertical line. Out of this huge infinite landscape, they all just line up perfectly. And this isn't just some quirky mathematical observation. Proving that they all fall on this line is so important that the Clay Mathematics Institute made it one of their 7 Millennium Prize problems. That's right, there's a cool $1 million waiting for whoever can prove it. But okay, why is a straight line of imaginary points worth $1 million? What's the big deal? Because if that perfect order is true over in the world of the zeta function, it forces a deep and powerful order back here, in the messy, chaotic world of prime numbers. If the hypothesis holds up, it gives us the sharpest possible tool for understanding how primes are distributed. It basically puts a leash on their randomness. We have formulas that give us a good guess for how many primes there are.
And this hypothesis tells us exactly how wrong our guess can be, and no more. It's a domino effect, too. Proving it would automatically prove hundreds of other mathematical ideas that are all just waiting, depending on this one big result.
So for more than 160 years, the greatest mathematical minds on the planet have thrown themselves at this problem and failed. It's become this epic, multi-generational quest, pushing the very limits of what we can think and what we can compute.
I mean, just look at how this hunt has evolved. Riemann himself, he checked the first few by hand. Fast forward to 1953, and you've got the legend, Alan Turing, using an early computer to check the first 1,000. And today, with our supercomputers, we've checked more than 1,000 trillion zeros.
Let that sink in. We've checked over 1,000 trillion of these special points, and every single one has been exactly where Riemann predicted it would be, perfectly on that line. But, and this is the brutal part of math, a trillion examples is not a proof. There could always be one more way, way out there that strays off the path.
And that leaves us right here, on the edge of our seats. Is this perfect, elegant alignment a fundamental law of the universe, woven into the very fabric of numbers? Or is it all just a colossal coincidence, a pattern that holds for trillions of examples, but will one day be shattered by a single rogue zero, throwing everything we thought we knew back into chaos? The hunt is still on.